Here I will present our work, called HyperCMR Enhanced Multi-Contrast CMR Reconstruction with Ego Loss. Task 1 Challenges: Recovering fine structural details. The K-space undersampling at 4 times, 8 times, and 10 times makes it really hard to capture those fine, high-frequency details in the images. Handling different contrast types. We have multiple contrast types like aorta, sign, mapping, and tagging, and each one needs a slightly different approach for reconstruction, which adds to the challenge. Generalizing to unseen types. In the test, we face unseen contrast types like flow to D and black blood, and the model needs to generalize well to these new data types without having seen them before. Task 2 Challenges: Reconstructing from different K-space trajectories. We deal with varied K-space trajectories like Gaussian, radial, and uniform, with acceleration factors ranging from 4 times to 24 times, which adds a lot of variability to the reconstruction task. Keeping the image quality consistent. Different undersampling patterns at different speeds make it hard to keep the image quality high across all scenarios. Background: Prompt MR architecture. Prompt MR set the state-of-the-art for cardiac MR image reconstruction. For the previous edition of this challenge, we base our algorithm on this innovative approach and suggest improvements. One big issue with Prompt MR is that it struggles to repairing the high-frequency information. The red boxes in the images help us see exactly where Prompt MR falls short, especially in preserving the high-frequency details we need for clear reconstructions. This lack of detail affects the overall image quality, which is super important for cardiac imaging since we need those sharp edges and fine details for accurate diagnosis. Background: Ego loss. Benefits of ego loss: preserves fine details. As shown in the first part of the diagram, ego loss starts with generating the gradient map, which helps in capturing fine details that are often lost in conventional reconstruction methods. These gradient maps highlight the high-frequency information, ensuring important structural details are retained. Enhances edge sharpness. Moving to the second part of the diagram, we chunk the gradient map into smaller patches and compute the variance map. This process enhances edge clarity by focusing on the gradients, which allows the model to maintain sharper edges, improves structural integrity. The final stage in the diagram applies a high-pass filter in the frequency domain, generating the magnitude spectrum. This helps maintain the structural integrity of the reconstructed image by filtering out unnecessary noise and emphasizing important anatomical details. These 3 steps, gradient map generation, variance calculation, and frequency filtering, all work together to preserve essential image features, particularly in undersampled K-space regions. HyperCMR optimizes and extends the existing Prompt MR framework. We start by fixing 16 central lines in K-space. SenseNet for sensitivity maps. SenseNet then uses this fixed portion to generate sensitivity maps, which help correct coil sensitivities. The undersampled K-space is transformed into the image domain using IFFT, giving us the undersampled image. We combine the sensitivity maps with the undersampled image to apply coil corrections. After that, we use RSS to create an initial reconstruction from the corrected image. PromptUnit then steps in to enhance this image, making it clearer and more detailed. The K-space is repaired during this process, recovering lost details. Finally, we get the fully reconstructed image, much better than the initial undersampled version. Key improvements include adding specific loss functions to recover high-frequency details, optimizing the model to focus on both low and high-frequency regions. This combination of losses allows HyperCMR to achieve a better balance, leading to more comprehensive image reconstruction performance. Data fidelity loss. This loss operates in the K-space domain and ensures that the predicted K-space matches the fully sampled ground truth, which helps maintain high-frequency details. SSIM loss. Working in the image domain. This loss focuses on promoting structural similarity between the reconstructed image and the ground truth, ensuring perceptual quality. Ego loss. Designed to enhance high-frequency detail recovery, ego loss applies a high-pass filter on variance maps to capture fine details in the image reconstruction. VGG perceptual loss. This loss encourages the network to maintain perceptual fidelity, comparing higher-level visual features extracted by the VGG network between the reconstructed and ground truth images. Regularization loss. A combination of L1 and L2 penalties in the K-space domain, promoting sparsity and smoothness to prevent overfitting. Final equation. All these loss functions are combined in a weighted manner to produce the total loss, with each weight fine-tuned to balance the different objectives. In the original Eagle loss, a Gaussian high-pass filter was used to preserve high-frequency components. In this work, it has been replaced with a Butterworth high-pass filter. The Butterworth filter provides more controlled filtering, allowing the model to retain more crucial high-frequency information, which is essential for CMR image reconstruction. This change results in better preservation of fine details without amplifying noise. In this work, additional optimizations were introduced for patch size and cutoff frequency. Smaller patch sizes, example 3, enhance finer details, but at the risk of amplifying noise. Larger patches, example 5, capture mid-level frequencies, ensuring a balance between noise reduction and detail preservation. The cutoff frequency of the filter was optimized to 0.35 for this method. Lower cutoffs, example 0.3, emphasize fine details, while higher cutoffs, example 0.4 or 0.5, are more focused on preserving structural integrity without increasing noise. Padding and other optimizations were applied to further enhance structural integrity during reconstruction, allowing for better feature preservation across different CMR modalities. These improvements, particularly the switch to the Butterworth filter and the optimized patch size and cutoff frequency, contribute to a more robust reconstruction, allowing Eagle loss to recover finer structures more effectively, especially in undersampled K-space scenarios. The dataset consists of multiple CMR modalities, including aorta, sign, mapping, and tagging, with each modality presenting different sizes. The dataset was divided into 11 groups based on these modality-specific dimensions to facilitate the training process. Each modality group has its own training setup, allowing for more precise control over batch size during training. This division ensures that the model can handle the different modalities efficiently. Training setup. We used a DEM as the optimizer. We applied a step LR scheduler. We used 8 steps of gradient accumulation. The training was done across 3 different GPU. We conducted experiments on 3 different GPUs. Task 2 experiments. We ran distributed training on for a 100 GPU. Batch sizes varied across the 11 groups. This is our result on the test set. Ours without Eagle loss shows significant improvement over the baseline across all modalities. By incorporating Eagle loss, our model achieves the best results across all metrics. Eagle loss effectively enhances high-frequency detail recovery, making the model more accurate and robust for undersampled K-space data. The visual comparison focuses on 3 CMR modalities at HyperCMR acceleration. Our message shows superior recovery of fine structures and high-frequency details compared to prompt MR. For example, in the sine-Levat modality, the yellow arrow highlights how our model preserves more texture and details. In the sine-Sax modality, our method demonstrates the ability to recover the K-space textures and overall image fidelity much more effectively. Task R2. The images show some example results. Masked K-space. This is the undersampled data we start with, showing missing information from the original K-space. Repaired K-space. Our model fills in the missing parts, making the K-space more complete. Predicted images. These are the final reconstructed images, showing clear details and structure. Overall, it proves our model can handle various types of undersampling and still produce high-quality images across different modalities. HyperCMR demonstrates clear improvements over prompt MR, particularly in recovering fine structural details across different contrast modalities and acceleration rates. The integration of Eagle loss is pivotal for high-frequency detail recovery, helping maintain the quality of K-space data even in highly undersampled cases. Our model consistently achieved high values in SIM and PSNR, with lower NC, showing its robustness across various imaging modalities and accelerations. The optimized loss functions provided a balance between recovering fine details and managing noise, proving to be highly effective for image reconstruction tasks. With these improvements, HyperCMR is highly suitable for real-world applications requiring accurate and high-quality CMR reconstructions, showing its potential for clinical and research applications. Thank you for your attention.